Welcome everybody who are in the room present at East Burwood and online. Special welcome to our guest speakers tonight, to Graeme and to Paul, and we look forward to hearing from you a little later and see how much I can remember and how much I've forgotten. Graeme and Paul, can I invite you please to make your presentation to the members? Absolutely, go right ahead. Thank you.
Righto, thank you. Thanks everyone for coming tonight, and hopefully we say something interesting and something some of you will know some of it and we'll know some of it, and we don't know everything, so bear with us. Yeah, who are we? Before we get into the title, well, I will say experiments with Quadrature mixers and DSP microcontrollers sounds really fancy, but we're just a couple of hams gonna give it a go and see what we can make using modern chips and SDR type technology with the emphasis on software. But I'll try and click that slide up. Who are we? We've been hams for 400 years now. We got our licenses on the same day, sort of during COVID 2021, during lockdown. I think the end of lockdown, or it never ended, but during lockdown. We thought, let's get our amateur licenses like we always wanted to do, and so we got our foundations, then we went on to get our advanced a few months later, because that seemed like a good thing to do. And here we are, standing up here, probably out of our depth, but we'll try and convince you that we know what we're talking about. You can find our stuff, our information on us on QRZ, like everyone else, I suppose. I should put these on so I can read it. So tonight's, we'll get into what it is. It's a radio, it's a transceiver, ultimately, with an emphasis on software, because that's our background, software. Paul, my son, is a software developer, as am I, always have been. Haven't really done anything else, except a hobby of electronics. So these days, it's a perfect combination. It's a perfect time to put the software to good use and program up some chips and do our version of what ICOM and Yaesu sell. It is ambitious. We're not trying to compete with them, but we want to do something. Why should all the handhelds you can buy, the Quanshangs and all those things, they don't have a nice coloured waterfall display, for example. We want one of those. We want it to be SSB. Not everything's F. There's so many FM radios out there. Yeah, we can do FM as well, but we wanted to do our thing. We thought there was a bit of a hole in the market. I'm jumping ahead a bit, but so we want to make something, and we'll tell you what that is. So, I'm doing this, or you?
Oh, you go doing this, yeah.
Hmm?
Yeah, you
go ahead.
Yeah.
So, what we want to do, we want to take this further than what that list is, but for now, we've got to limit the scope, or we'll never get anything done. Like the usual project, you always dream of all the great things, but you've got to tie it down to something achievable. So this is some of the things we started thinking about. Just a 2-metre transceiver, other bands later perhaps. I always wanted a nice coloured waterfall, because I'm a Yaesu guy and I haven't got a radio with one. I thought the first one I'll make one myself, because I haven't got a 7300 or anything like that. Paul's the ICOM man, and he's got that sort of stuff. But a touch screen, I want one knob on the top. Don't want a whole lot of knobs and buttons. One knob, turn it on, push it, maybe squelch, long push, turn it off again. Or, volume and squelch, and a push button. Keep it simple. A touch screen to set the frequency on the waterfall. Some extra buttons to go back and forward, fine tune it to get your frequency. That's the sort of thing I want. We want ultra low standby power for various reasons we'll talk about. Probably Bluetooth, and maybe a web server on one of the cores, on one of the processors, so that all the settings that we build into this, you can go to a web page on your local net and set and explore, and maybe even control the radio remotely. That's getting ambitious, but maybe you can plug this thing into an antenna somewhere and control it from your laptop somewhere else. USB-C charging, transverter interface for maybe this thing could be used as an exciter for other frequencies, other bands. 10 plus watts, I mean, we don't know, arbitrary, want some power out. We don't, something more than 5 watts, everyone makes a 5 watt one, we want more. So we'll need a good battery, I guess. And lots of modes, but we're emphasis on SSB for us initially, but other modes. In the digital realm, other modes are easy to achieve. Once you've got a framework with these pieces in place, or you know, the display and the user interface and the radio part, once it's all in software, other modes are fairly easy to achieve. So that's what we, in the beginning, what we started toying with. We've been pretty slow to get to where we are, but there's a lot of, life goes on. We both work full time. I've just moved house. It took months. I'm making excuses already for why Paul's done most of the heavy lifting, but we'll see. It'll pan out in the wash.
I think we started thinking about this, what, 2, 3 years ago?
Yeah, 2 or 3 years ago. As soon as we got our license, I said, where are all the 2 metre SSB things that I used to dream of? I want one. Baofeng haven't got one, or they haven't got one. We have to make one. And I ended up buying old radios that drift just to get on 2 metres. I think I ended up with an 818, okay. I can get on up there with a shack in a box, sure. But we want to do our thing because we're hams and that's what we do. Where are we? So ultimately, for now, a 2 metre handheld SSB transceiver with waterfall display, SDR, everything, all software defined, is the goal. Why? I've already mentioned why. Some of these are expensive. It's a great learning exercise for us. That's part of what amateurs do, isn't it? Tinker, learn, share. So sell, maybe, for us. We'll see. Initially planning a conventional superhet for about 5 minutes, but then, because I live in the same suburb as VK3PA, and I think he's done everything to do with everything, so I didn't want to make a conventional radio out of 2 components like he can. Hi Peter, if you're listening. But I've moved down to Mornington now, so it's all his, the seaside and the Chelsea anyway. But we got inspired we thought, we're software guys, let's do software. We're good at it, and if we can just get some of this electronics tied down and get those chips talking to each other, I'm sure we can program it to do some fancy stuff. And that'll be where the months go, I'm sure, making it all work smoothly and ironing out the bugs from the software. But and we got interested in IQ modulation, which we'll get into the why we're interested in that. I think you want to talk here, Paul.
Yeah, I can start talking about this.
Paul got into the component side more, and you'll see the small thing I did shortly.
Cool.
I've just been clicking through with the wheel.
All right.
Yeah. Thanks, Paul.
Hi, everyone. Okay, so we started thinking about, we've got RTL SDRs. You can pretty easily do a SDR receiver. Where's the transmit? How do you do that portably and at low power? So we started thinking about what components are out there. So I got on the traditional suppliers of electronics devices and started just searching by parameters. Okay, what are the RF chips that are out there? And I thought, well, mobile phones somehow magically can transmit on whatever band, and yes, there's billions of dollars of engineering that go into that. But there must be some chips. Maybe there's old Wi-Fi chips that have a test mode. Maybe there's Bluetooth chips that can modulate something, you know, at 2.4 gig, and we could mix down. Who knows? So I started looking. We were keen to use the ESP32 as an MCU, right, to do DSP and everything, because it has Wi-Fi and Bluetooth. Seemed like a no-brainer. However, probably jumping ahead, I don't think it's ADC, analog to digital converter capabilities are that great, but it's great for the Wi-Fi and Bluetooth. So then we discovered, obviously we discovered in the literature, quadrature mixers and the phasing methods. So just jumping down to the bottom, some of the background reading, I found a copy of Solid State Design for the Radio Amateur. It's a famous book at a Hamfest. And it's just reading up on phasing, and I'm looking at the description of IQ modulation, which is used for digital modes typically, and I'm thinking this is the same thing really, especially if you do it in software. So then we headed along to Friedrichshafen and went to one breakout presentation there, which was amazing.
Friedrichshafen is the big Hamfest in Germany, in case you don't know. You probably all do. There's Tokyo, isn't it? Dayton, and Friedrichshafen's about the third biggest, isn't it? Anyway, just thought I'd jump in case you don't know what Friedrichshafen is.
Thanks for the background. Yep. So there was a presentation on a transceiver to talk to the QO100 satellite that they've got up there, and that used some of the same principles, and that made me think, well, we might be on the right track. This might actually be viable. So yeah, that was inspiring. The other book I referenced there, Digital and Analog Communication System, I think it's a textbook. It's a tome of maths, and I think if you read more than about 10 pages, without a maths background, you'll go crazy. But there were some good ideas and sort of theoretical foundations in there, which I referenced. So I don't know if you can read that, just an excerpt from the book. And you'll see this diagram a lot in any kind of discussion on IQ mixing. But basically, if I can use the mouse cursor.
Yeah, it comes up. Yep.
Yeah, this is theoretical background. I'm not going to do the maths because I don't understand it. But on the far left, you have your IF signal coming in. So your intermediate frequency, that can just be your RF, right? Or you could have mixed it down first. And that gets fed into two balanced mixers, which are these circles with the X. So the balanced mixer gives you the sum and difference of your two input frequencies. And the good thing about the balanced one is my understanding is it suppresses your local oscillator in the output. So there's two of these. And then the local oscillator for each one of them is just your straight oscillator input, and the other one gets shifted 90 degrees before being mixed, which gives you two different mixing products, and that's your I and Q channel. So one is in phase, one is 90 degrees out of phase. And then that's, in this diagram here, then they go through a low-pass filter, which I didn't initially think was important, but it is important, as we will find out. And in the text he's saying your IF filter, so traditionally that would be at your IF frequency, it could be 455 kilohertz or wherever, but here it's a zero IF receiver. So your IF filter is actually just a low pass filter rather than a band pass filter. So that's the principle we were kind of working from and evolved this design from. So I sort of talk about this in the receiving sense. The transmit side is the inverse of all of that. Were you going to talk about this one?
Oh, just the guy. Oh, well, yeah.
I'll just stay here because it's a brief one.
We went to Friedrichshafen to look at all the stuff, all the junk, and dream about carrying it home. Of course, we can't bring it home. We're in Germany, but there's everything there. It's aircraft hangars full of stuff. But we just went to one lecture, and there was tens, or I don't know about hundreds, but many tens of lecture streams. We happened to go into one. Okay, we picked it because the title was interesting, based on what we were dreaming of. And this guy almost starts talking about the scope of stuff we wanted to do, but with some variation, of course. And as soon as he puts these slides up, we think, hey, that's almost what we want to do. And it inspired us. It just helped us. Like, we come back to Melbourne, right, let's get into it. We're going to do this. And you've tested with this chip, I think.
That chip was already on my radar to get a sample of and try and build something.
So I think it's, Baris Dink. So credit to this guy for inspiring us. You can look him up. Anyway, I just want to mention that. A couple of photos I snapped because I thought that's us. Maybe.
Yes. So still in, this was 2004, July. I was still in Germany at this time, so just noting down some ideas. I won't walk through this whole thing because we're going to rehash it a little bit later anyway, but we basically had the ESP32 controlling a display. Thought we might have a keyboard, some switches, maybe a GPS input, just sort of dreaming here, right? ESP32 doesn't natively have good analog capabilities, so I thought we'll get a digital to analog converter chip. We'll find one of those with 2 channel outputs, one for transmitting your in-phase signal, one for the quadrature signal, there's your IQ, and conversely, analog to digital converter. And I thought, well, we'll have one stream through a narrow filter, which will demodulate as our SSB, and the other one, because we were looking to get a waterfall display, would be a wider filter. And the ESP would talk to those chips digitally. And then the SI, 5351, we thought we could use that as a local oscillator, also digitally controlled, give us a 144 megahertz output. And then the other idea had keeping the software theme going. I didn't want a radio board full of adjustable analog devices. I thought we could put digital potentiometers around the place, and they would feed the bias voltages and filter the bandwidths by changing the resistance, and so on. So that's the digital sort of side. And then the other scrap piece of paper here is the analog side. Okay, I guess I'm going into some detail. So
Yeah.
transmit side,
Sorry, go on.
yeah, and this is just talking basically an implementation of a low-pass filter and using those modulator chips. I've got a much nicer diagram coming up.
I'll just jump in and say
yeah.
thank you. Thank you, Boris Dink, because it took Paul 5 minutes after coming back from Friedrichshafen, and he comes out and shows me these diagrams. I think, yeah, he's got inspired. Even if it's not what we've ended up with, I think, yeah, something's got in here.
I was thinking, well, we'll make a similar thing with using the ESP32 rather than the Arduino.
Yeah.
So,
Was that next slide for me?
so this is,
Oh, here we are.
you may be sitting there thinking, well, how many screens have we got? This is kind of the table of contents of what we're going to talk about next. We took all these ideas and we just started experimenting, making some prototypes. So we'll spin through those.
Oh, yeah, no,
That's you now.
I'll just back one. I'll just, so there's a diagram, the bottom bit, we do want to use an ESP32, but not to do anything really radio, really only to control the waterfall display or to generate it, and to tell the radio chips, which are more powerful ADC-wise and DAC-wise, what to do. What are the band limits? What bins out of its FFT, fast Fourier transform, is it going to give me to put on the waterfall, which we'll get into later. So we are going to, I did a PC-based prototype, and that's the sort of thing, it's a bit crowded actually, but a bit less crowded on the text, but that's the sort of thing we want to have on our cheap yellow display. I'm not sure if you're familiar with those. This is just a battery pack, and that's the, I don't know if you're familiar with these, you might have seen them on AliExpress. They're an ESP32 with they're yellow, and it's all a CYD, cheap yellow display. And it's got everything there, plus a 240 by 320 display. So that's sort of what we want, that size in the radio. And you have most functions through there. It's a touch screen. It's a bit, we may change that. It's a bit ordinary, being a resistive touch screen. You've got to really, it's not nice like a modern smartphone, perhaps, but cost comes into it, you know. We've got to start somewhere, so this is only a battery pack to make out. I've been doing some work. I got the, I don't know if you can't see it probably, but it actually is running a waterfall, but it's just with some test bins as though they came back from a fast Fourier transform with 3 test signals. So nothing's coming into this. But it would come from the radio. I'd say I want from 144 to 144.3, and I'd display across there, you know how waterfalls work, I think most people, plus the signal strength at the top. All that comes from, I'm jumping ahead too, but anyway, I knocked up a demo and now I've got it working in a test mode on one of these cheap yellow displays. Can be done. But that's the ESP32. And we'll also have our speaker and microphone and Bluetooth and web server going through that as well. I'm probably jumping ahead on the ESP. What else have we got next?
So I'll talk about the modulator, and then
I'll get back to this after.
Then you can talk about that some more.
Yeah. I'll just watch that.
Okay. So IQ modulator, where did I get to with my experiments? It sort of works. So I can, using test equipment, I can generate a signal. I can see some modulation happening. And I'm confident from what I've seen with some more tweaking, I can get modulation working. So it's based around the analog devices 8345 Quadrature modulator IC. That chip is fairly expensive for a single one. I think it's about $20 on official sources. You can find it cheaper on eBay. Is it genuine? Who knows? But I got it from there and it seems to work. Although maybe that's why it only sort of works. There's more experimenting to be done. So the specification for the chip is 140 to 1000 megahertz. And it can output signals outside the range, but you'll get more carrier or local oscillator leakage, and your sideband suppression doesn't work well. The further outside that band you are, the worse it is until it's just an AM modulator. But that's interesting because if you build a radio for one thing that works perfectly, can you get it to work somewhat on other bands? It might be useful. For me, this was new. Every input is differential. What does that even mean? Like you have two signals and they're complementary rather than everything being referenced to ground. So just following the example circuit in the datasheet, I put in a small balun for the local oscillator so I can give it a single emitted input and it would create a differential output to drive the mixer. And then even the baseband IQ signals, so your audio sort of signals, a differential. So I built an op-amp based circuit to convert that because the datasheet recommended it, but I didn't really notice much difference compared to just leaving the negative differential inputs at DC. It's not recommended to do that, but the op-amp also made it much easier to adjust the bias levels. So there is an alternative I've since discovered, which might be this ADL 5385, which has an even wider band. So you could potentially, here's where scope creep comes in, right? Because we're thinking we'll make a 2 meter transceiver, but I'm already racing ahead and thinking, can we do 6 meter, 2 meter, 70 centimeter, 23 centimeter? What can we achieve? This one is a QFN, so it's a much harder package to solder, and it requires a 2 times local oscillator frequency input. So for a 144 meg signal, you would need to feed it 288 megahertz, which is more challenging, and the chip is slightly more expensive. However, I am planning to do another experiment with this, so stay tuned. Delving in further into this analog devices chip, on the left is the functional diagram. So if you remember back to the photo of the textbook with your dual balanced mixers and 90-degree quadrature local oscillator, this chip achieves that within one package. It has a phase splitter for your local oscillator, and your 2 mixers and a summing circuit, which is buffered. On the right is the evaluation board schematic. Analog devices, for some reason, charges more than $200 for the evaluation board. For a $20 chip, I thought it would be easier just to build it using that circuit. So that's what the photo on the right is our implementation. The board containing that is here. You can come have a look afterwards. But it's tiny. It's a tiny part, right? That's a 16-pin chip. in a SSOP format, which means the whole chip would fit under my fingernail. Sorry, the microscope's not working. Can't show you that. And it's flipped compared to the diagram. So where the mouse cursor is on the bottom right, that's pin 1. Local oscillator input is here going through this balun, which I'll talk more about soon. Okay, here it is in kind of context. I have a board with this chip and others, and basically wanted to break out every connection into a separate SMA connection. So I can play with it. So power going in here, local oscillator being driven in this case by the tiny SA in frequency generator mode because it's nice and portable and handy. The Quadrature inputs are here, coming from my breadboarded op-amp circuit, which I will show you separately. And then the output from that goes into whatever you want to test it. In real life, it would go into a power amp and a filter. And here I've tried various things. I've put it into a spectrum analyzer. I've put it into an RTL SDR. I've put it through a sort of dummy load. I forget the word. Something that reduces the signal to a safe. An attenuator, yes. Put it through an attenuator into a transceiver and didn't blow up the transceiver, so I was happy with that. So that's the sort of test setup of the modulator. Okay, the differential, drive, and bias. So on the left is my original circuit. I use a PC sound card because it can output 2 channels of analog signals. That's on the left, so signal from the PC, should say from PC, not to PC, but got your left and right audio, adjusting the levels using potentiometers, and then AC coupling the audio in. So the pots actually set the bias level, which is the DC that the AC waveform sits on top of. And then for the negative differential inputs, I'm just biasing them to a DC level. It was very finicky, as you could probably tell by how many resistors I've got hanging around. But it sort of worked. Then I started playing with op-amps. Before this project, I never used an op-amp. It was all a bit mysterious. So probably in the last few weeks, I added this actually. I just found some old chips, some LM358s. They're okay. I ordered some other types and just started playing around, and ultimately built this circuit, which will be part of the next iteration of the printed circuit board, so it won't always be on a breadboard. And this lets you, the chip wants about 0.7 volts DC bias level, which sort of matches a diode's voltage. So all I've done is bias each one to positive voltage through a 4.7K resistor, and then through a diode into ground. And that holds it at about the right level. You can tweak the local oscillator feed through by tweaking the relative levels of all of these. So in the final version of this, whenever we build that, that's where I'd want to bring in things like digital potentiometers to tweak the levels and sort of have the radio automatically calibrate itself. More experiments. So I took it out to the garage where I have these lovely big old HP machines.
Can I just say something?
Yeah, go.
So all this stuff here, this junk we buy at auctions, that people sometimes say, what are you going to do with that? You should see Paul's garage, and we're actually putting it to good use, some of this stuff. So there you go. It's not going to the boat. You know, it's not connected to the end of a chain on the boat. It's actually getting used. So, yeah.
Yeah, thanks. I had a lot of fun, firstly repairing these things because they weren't fully functional when I got them, but that's a story for another day. Had more fun hooking the signal generator up to provide a local oscillator, just see my mouse cursor there, and then there's an audio oscillator sitting under the board. So I'm just feeding one of the channels just with audio, which means I'm not getting that quadrature modulation. It's more like AM, what comes out of it. And I forget what frequency I'm at here, but I think I tested it on pretty much every emitter band up to 2.4 gigahertz. And I can get AM modulation out from 7 meg to 2.4 gig. But to get SSB without the carrier being a massive spike is probably much more limited. But that's a test setup. The spike in the middle is a carrier, and these other spikes are the audio kind of beating with the sweep speed of the spectrum analyzer's oscilloscope. So I'm getting something out, which is great. But it's pretty crude. It doesn't tell me, okay, can I actually get upper sideband if I only wanted that? So that's when I hooked it up to the 9700 and used it as basically a detailed spectrum analyzer. So I'm attempting to create upper sideband. So I crafted some audio files by recording my own voice in one channel, and then that's this one. And then in the next one down, that is the same signal, but every single frequency is phase shifted 90 degrees, which I did using a Hilbert transform plugin in Audacity. So I played that out the speakers into the mixer chip, and this was a result. So if you've ever had an SSB conversation and looked at the waterfall, you'll see a lot of energy if it's upper sideband above your center frequency. So the white line in the middle is your center frequency. So here you can see there is a bit of unwanted sideband on the left side, and there is a bit of carrier coming through as well. So still working on that, and then below that, that was a separate test, because I had a file that was doing double sideband, then left, then right, lower, and then upper. But it sort of looks like it's getting somewhere. And there's some neater screenshots from the device itself. On the left, here I am mucking around with potentiometers, tweaking 4 different things to try and get the minimum amount of carrier leakage. So here it's mostly confined to lower sideband, a lot of carrier, and here I'm getting some success in actually reducing that. So yeah, just having a play, and that's all at 144 meg. Now back to Graham's cheap yellow display.
Oh yeah, okay. The cheap yellow display again. Well, the ESP32, really, the display is just the display. We could use a separate one, but I'm using the one integrated on that board. We're going to do all the GUI, or the graphical user interface, in our world on one of those using an ESP32, as I mentioned earlier, with a touch control, band span, and center frequency. I don't know if we'll be able to stretch it. We probably, to get the limits with that cheap display, we might have to just use buttons to set the band limits for the sweep, for the spectrum. So the ESP will set the center frequency, or the operator will set the center frequency for sure, one way or the other. And I'll send that to the radio part, the real radio processors, and it'll send me back a byte array of frequency bins post fast Fourier transform, FFT. We don't have to worry about what it does. A lot of you already know what it does and what it is, but we won't go into any details. But if you put in a time-based, what are all the frequencies, you get amplitudes of each frequency back to a certain resolution. So that's what you'll see on your waterfall display from one frequency to another. I had a lot of this frequency, I had none of that. I had a lot of noise, I had another frequency there, or some, you're fairly familiar with that. So the ESP is going to get that back from the radio chips. It's all a radio, but this is the GUI side of it, the graphical display. And it's going to just take each one of those and plot it across the screen as a signal strength, number one, because they're 8-bit bytes, so we'll get a value from 0 to 256, 255. And it'll draw one line of the waterfall. And then next time it'll say, I want this again. I want these 20 times a second, say, to get a nice smooth waterfall, a nice frame rate. And I'll push the whole display down and draw the next line. And that way you'll get your waterfall. Push the whole display down, next line. So that's how we're doing that. It's a dual core. I'm not even sure if the cheap yellow display is a dual core, but we want a dual core ESP32 because, as I mentioned earlier, we would like to have a Bluetooth. I don't know if that needs a core, but we want to have a web server in there to serve up all this stuff to a web page on your laptop. There's also an ultra-low, I don't know if people have played with the second core on ESP32s. Most people just get LEDs to blink and sense temperatures and control actuators, and they don't even bother about the second core. There's another whole core there of processing core. There's actually a third core, the ultra-low processing core, which most people never touch. And I don't think you can program that easily through Arduino software. There's a tiny compiler, a tiny assembler, I think.
You can do it. It's hacky.
It's hacky, yeah. You're back to almost assembler just for its 24 instructions. And with the ultra-low processor, you can put the rest of the ESP to sleep, which can put the rest of the radio chips to sleep, and it can still monitor some GPIO pins. So you can have even turning the radio on, or maybe a real-time clock. You could set, I want the radio on from this time, off at this time. Or you could sense some things. You might have some other radio receiver, and it gets a signal, and you can feed it in somehow to this thing, and it wakes up your radio. I don't know yet. But it draws microamps as compared to hundreds of milliamps for the ESP when it's doing anything. So it's good. We'll see what we can do with that. But it's actually a 3-processor. There's a small processor and 2 main cores, and we intend to utilise all of them for the graphical user interface, the bit you see, the flashy bit. That's about it for. Oh, yeah, that's what I've said. What have we got?
You want to talk about this, or should I?
No, I don't even understand that.
All right.
No, I do. I'm trying to understand some of this. I don't even understand what 0 IF is yet.
Yep.
I'll ask you later.
That might be a gap in my...
Not now, just talk
not
about
now. Okay. I should talk about that.
Yeah, but we'll
Okay.
get through these a bit.
We'll go through it.
A
Yes, quicker.
Yeah.
Yep. Okay, the demodulator is the converse of the modulator. It's also made by Analog Devices, and this is the chip I'm looking at. And what I didn't read careful enough in the data sheet was that it needs, like some others, a 2 times local oscillator frequency. So my dream of using the SI5351 is probably not going to cut it. Maybe I could use a frequency doubler, so a transistor with a tuned circuit in its collector. That would lock us on to a pretty narrow band, and might be interesting trying to build that. Or there's another chip, another synthesizer chip, that's good for up to 4.4 gigahertz. So that would actually work up to 2.2 gigahertz local oscillator, which is more than what this demodulator can do. That might unlock using a different demodulator chip, which goes up to 2 gig. Future experiments.
As you can see, excuse me, Paul. Okay. It's early days, so we're doing a lot of trying of chips. I guess that's why we're going through some of these, because we go down roads. You know, oh, hang on a minute, I can't use that SI53 oscillator because of this. So it's a bit of a road of discovery for us to try some of these things. So I guess we won't dwell on them too much because we'll probably change some of those anyway. There'll be some reason we have to go to another one. But eventually there'll be a path through all this, hopefully, and we get a radio.
Yeah. Or maybe there is a way to use the SI chip, so maybe there's some hack someone knows, so let me know. Okay, so the diagram for this chip, again, evaluation circuit, I took that and said, cool, what's this thing? That's kind of intimidating. I can't even get that part. Or can I? What if I just search it? Yes, I can. I can buy that little ETC balun thingy, and I can just solder it to my board. So I did. Here is the implementation of that circuit, according to me. And things I wasn't quite sure of, I just broke out into 2.54 mil headers, so I could play with them later. Ended up, I just needed to jumper some things to get it going, which I'll talk about. There's that surface mount balun. You could probably wind your own if you wanted to. I thought about it and thought, no, I'll just do what the data sheet says and experiment with that later. So there it is. What it kind of looks like. So I set up some test signals, so I would tune to 144 point something, and I'd put a tone 1 kilohertz away from that. So I've drawn these red lines, right? So again, here's your left-right audio corresponding to your I and Q. The signals are the same, but the phase relationship between them is different. And I always forget which one's upper and lower, left and right, I and Q, but it doesn't really matter, because if you get it around the wrong way, you just get the other sideband. So yeah, hopefully you can use your eye on that red line to sort of calibrate, okay, where the peak of one sine wave is and the bottom of the other. So that in this one, the peak of this one, of the bottom one, is before the bottom peak of the top one. And in this one, it's the other way around. So when we use 0IF, there's no filtering that can cut out one sideband, because they're both starting at 0 and going up to whatever your bandwidth is. So if you want only one sideband, you have to do that using some phasing tricks, which we want to do entirely in software. And here it is, I'm just stepping from one to the other. And this huge big thing in the middle is when it's very close to the signal is pretty much right on the local oscillator frequency. But that's cool, because it gives you a nice visualization of the 90-degree phase difference between the two signals. Okay, so the low-pass filter turned out to be important because this chip has something, I don't know, was it 50 or 70 megahertz bandwidth. So I think, okay, I'm going to put 144 meg, I'm going to mix that down to 0, but then I've got 50 megahertz either side of that. And if I just feed that into the PC sound card, I get a whole lot of interference from broadcast FM, because somewhere in there is the signal and it's demodulating. So you actually need to bring that IF bandwidth right down to just a few kilohertz if that's the signal you're interested in. So I started building another op-amp circuit and putting some capacitors in there to build a low-pass filter.
Those solder blobs,
Yeah,
they're not blobs.
I'll get to this on the.
Yeah, okay.
I'm still on the left. This is baseband filtering.
Yep.
So the neat thing about this is a low-pass filter at audio frequencies. You can build it using an RC circuit instead of an LC. In fact, you wouldn't want an LC circuit because your inductance would be huge. And that means you can control the bandwidth if you can control the resistance. Then the other part of filtering, I thought, well, I better filter the input as well. So I quickly had a go at designing a 144 meg filter. Mixed results. These holes are 2.54 mil apart. There's a black component here. Probably can't see it, but that's an inductor. So it goes inductor, capacitor, inductor, capacitor, inductor, capacitor, inductor, capacitor. And then they're all in series, and then in shunt, it's a whole lot of capacitors. And I just use a tool that I found online to design that. I put a link there. So you put in what type of filter you want, the architecture of it, the values, and it gives you a suggested circuit diagram with values. So I just sort of built that visually by soldering these components. So yeah, they're not just blobs, they are components, and these are SMA connectors on the left and top. How did that work? Well, I plugged it into the nano VNA to find out, and it actually kind of made a bandpass filter, which was cool. But the frequency is not where I want it to be, and it's pretty lossy even at the least lossy point, in my opinion. But you could overcome that with more gain. But 144 meg is off on the side here. I really wanted it centered. It's a bit low in frequency. Why is that? Could be something wrong in the design. Could be component tolerances. It could be that I just used the cheapest components I could get on AliExpress. Or it could be the physical layout's not ideal for it. So I can experiment more with
Could be
that.
those solder blobs.
Could be the solder blobs, the non-impedance controlled
Capacitance
circuit
and
board,
yeah.
straight capacitance lowering the frequency, probably. But yeah, so we need some filters. That's still in progress. Now for a rapid shift away from the RF domain, talking about microcontrollers. So as Graeme has hinted, there's something in between all this RF analog stuff, modulators, demodulators, and then the ESP. And in there we want to put another microcontroller that's got a lot of analog capabilities. So we explored a few options. This one came up in my early component search, the EFR32FG14, also known as the Flex Gecko from Silicon Labs. It's an RF system on chip. It does 2 gig and everything from about 140 meg to 1 gig. And everything in this circuit, in this diagram, is within the chip. And there's a whole lot more, but this is just the RF part. So if you look at it, just looking at sub-gigahertz, it's already got a lot of what we thought we might need. It's got an amp, it's got IQ balanced mixers, it's got a power amp, it's got an amplifier, it's got a bandpass filter, and it's got an ADC. And same thing for 2.4, but we won't worry about that for now. So the first question, can we actually access the output of the IF ADC? And there's spoilers, because this is a PDF, so it's all come through at once. Yes, there is a test mode, and it fills a buffer with alternating I and Q samples. So that could actually replace the demodulator and analog to digital converter right there. How good is it? I don't know. Haven't really got the code to work, but I'm working on that. Can we transmit IQ samples? Sadly, no. It has the IQ for the receive, but you'll notice that's not hooked up to the PA. So the PA is just a frequency synthesizer, and the modulation is just basically FM. It's for digital modes. There is a test mode that can transmit a carrier, so we could use this as a local oscillator and have still an external modulator for transmitting. Yeah. So that's one option. Okay, first, I put this here because a lot of people will put on Instagram or whatever, they'll work at something for a year and say, hey, look, this is my first attempt. And I don't want to do that. My first attempt at soldering these tiny devices was probably very naive, and it didn't work. So I just inverted it, tacked down the exposed pad, and then tried to solder very fine wires. And I tried to use a multi-DFN sort of adapter. I just got solder blobs everywhere. I hated it, so I coughed up the money and bought the module, this thing. And then I tried to program it using an old board from the same company designed for a different chip. That sort of worked. I've got it here, you can have a look. And I got Hello World for microcontrollers going, which is a flashing LED. And I also got it to transmit a signal at 144 meg. But I lost the photo and screenshot of that, but it was pretty cool. So there's hope there. Generally, we're looking for microcontrollers that have a dual ADC and DAC, because we want to sample or create the I and Q values simultaneously. Maybe you could hack your way around that using some more complex software, but it's complex enough. It needs to have enough bits, maybe 12 bits. How much is enough? Who knows? Sample rate depends how big we want the waterfall. If we're talking, well, we want a 500 kilohertz waterfall, we probably want a 1 megasample ADC. And it's got to have enough computer power within that microcontroller to run the software to actually run the fast Fourier transform, generate the waterfall, demodulate, and modulate. So we already talked about EFR32. It's interesting just because it's RF. It's pretty underpowered for the price otherwise. It's an ARM Cortex M4, runs at 40 megahertz. Costs about $16, so pricey. PIC32 AK1216, I discovered this year. I think it's fairly new, and it's based on a DS-PIC33. The data sheet claims it has 2 channels of analog to digital conversion, 12 bits at 40 megasamples. I need to test that because I kind of think, is it really just 40 megasamples at 8 bits? And if you want 12 bits, you have to reduce it. We'll see. Only got a single digital analog converter. That might be a showstopper. We might be able to work around it. And it's very fast, 200 megahertz. It's got dedicated DSP instructions. And that whole thing costs $3.45, which is a fraction of what a dedicated ADC chip costs. So why would you buy a dedicated ADC to plug in to your ESP when you can just add an extra microcontroller for less than $4? PIC32CX, completely different chip, but microchip, the manufacturer just likes to call everything a PIC32. It has 2 12-bit 1 megasample ADC, perfect. 2 12-bit 1 megasample digital analog converter, perfect. 120 megahertz Cortex M4F. The F means floating point extensions, so it's good for DSP stuff, and that's about $4. Even if you buy one, you can log on and buy one. If there's not enough power in there, fallback plan is to look at some STM32s. I already bought a dev kit for this one, the H533. It's an ARM Cortex M33, which is faster per megahertz than the M4, and it's got about double the performance of the PIC32CX. And there's bigger, more expensive ones. If we need more, I don't think we'll need more compute power than that. Some custom PCBs, sort of saw this one before, but all these things have footprints that are hard to work with. So it's a matter of, okay, do I get adapters to Julian ion packages and put them on a breadboard, or do I just start actually designing the circuit and get it manufactured? And I chose to do that because I've done enough breadboarding in my life. So I put the modulator, demodulator on a board, and I put a couple of the PICs on the board. Why didn't I just buy a pre-done board from Microchip? Because they wanted to charge $100 and something for a carrier, and then you had a special module that carried this chip, which would cost another $30 to plug into it. I mean, the chip costs $3. Why can't I just do this? So I built this, and then I realized it doesn't have a bootloader. It needs, well, I made provision for that. I put the header for the PIC kit, the programmer, because I have a PIC kit 3. I thought I'll plug that in. It's going to work great. But the PIC kit 3 doesn't support this chip, so I had to buy a PIC kit 5. So I had to pay anyway. But now I've got it, and I can build as many of these different boards as I want. And it was fun soldering them. Probably took me 20 minutes to hand solder this
I don't think I could do that. If you come and have a look at these boards later and have a look at the size of those chips, that's soldering. I don't think I'd come near it. And can I just say about the boards? Just jump in.
Yep.
As Richard said in July, you know, you can get these boards made. The dearest part's postage.
Yep.
If you can make the board, you've got the tools, you do the software. If you're confident about getting the chips on, they're cheap as. And you try to buy Australian, but they can't compete. It's so expensive, and all you do is pay a postage bill and a board cost, and they come around in what's the turnover?
Depends how much you want to pay for postage. It can be less than a week if you get it couriered,
Yeah.
or you can do the slow.
So
mode.
it's so why wouldn't you, if you can solder them? Why wouldn't you do this? Why would you buy a development kit when you can just keep iterating and making your board better and better and better? So sorry to Paul.
Yep.
I've experienced that before with the Chinese board makers, and they're brilliant boards. I think that's a 4-layer board, right?
The green ones are 4 layers. Yeah, the blue one's 2 layer. Yeah.
You understand how they can do it.
Yeah. Mass production, or maybe they're loss
Steal
leaders.
the market and then put the price up when everyone else is out of business, maybe. You
Yeah.
know? Says the cynic in me. Yeah.
Yeah.
Been doing it for a while.
Yeah. I know, yeah. Sorry, Paul.
No, you're good. I have many side issues I could jump into, but in the interest of time, I won't. But yeah, happy to talk about it more. Just to say also that I did start getting stencils made for these and putting them in the oven, and that was even easier than hand soldering. Okay, what tools did I use? PC audio, we sort of talked about. I don't need the microcontrollers working to be able to start experimenting with the IQ, because I can just use my desktop PC as a substitute. Receivers to test the modulation, talked about these already. Also used the HP 8555A spectrum analyzer, just to look at the harmonics, because your transceiver is not necessarily going to go high enough in frequency to see that. And signal generator to create the local oscillator. The HP signal generator is massive. It's a 2-person lift, and it's noisy, but it does a great job, and it's really fun to play with. The Tiny SA has a signal generator. It'll get a frequency where you want it, but it's very noisy, and it's also quite low level. And the Nano VNA puts out a more powerful signal. You can just set it to a CW frequency, so that's useful. For the oscilloscope, I ended up using a portable oscilloscope. It's multimeter form factor. It was about $50, and it's good enough for audio. It'll go up to megahertz, several megahertz. And a coaxial attenuator. This is a game changer. Used to be a little bit naughty and just like touch my finger on something transmitting and pick it up from the air, but it's better to just couple it coaxially rather than risking creating interference. Not that it would at these milliwatts. So that was the tools used. Do you want me to go through this, Graeme, or will you?
Oh yeah, interest of time.
Yep.
Yeah.
Okay. So this is the overall what we're aiming to put together. I said there was a neater version. This is it. I'll zoom in. Just starting from the top, the ESP owns everything human related, right? Your speaker, your microphone, your display, your communication over Bluetooth, Wi-Fi. And it just talks to the what we call the RF microcontroller, and it says, give me this band as a waterfall, give me your audio, or transmit this audio on this frequency. And, jumping down, so then we've got this microcontroller ones we're just talking about, and it can use its DAC to output signals through low-pass filters to remove step artifacts on the DAC. Goes through an op-amp circuit to give you a differential drive into the modulator. Meanwhile, the modulator can be enabled, probably saves about 50 milliwatts when you're not using it to switch it off. The local oscillator drive can go through a balun, or if you've got a synthesizer that puts out a differential, like that 4.4 gig one we're talking about, you wouldn't even need the balun. The RF out from this, it goes, here's the transmit path, but before we get to that, it's just joined to the RF in, because then the demodulator can sample that at the same frequency, and the microcontroller can basically sample what's going on. And this can go down to DC as well, so you get a DC level, and what that will tell you is how much carrier is coming through. And so you can adjust the bias levels and things to optimize your transmission. And we want to write software to do all this. I think it's pretty ambitious, but we'll try it. So then when we want to transmit, we enable the power amplifier and we switch off the receive. I don't know, that will be a relay or some component to be determined, but bandpass filter to keep it clean, through the power amp, through a low pass filter again probably, and then out to the antenna. And then for receive, we switch off the power amp. We switch on the receive path, conditionally switch on the preamp if we want that. It probably forms part of the AGC. And then that comes through the bandpass filter, straight into the demodulator. And the demodulator has a gain voltage set from the microcontroller. So we might make this sort of an analog loop, but I think we can do it in software. And that forms your AGC. So if the microcontroller is seeing very high levels, it's clipping or getting overloaded, it will reduce the gain that's inherent in the demodulator. And these op-amp circuits form two purposes. One is to convert your differential to single-ended for the microcontroller, because otherwise we need basically 2 extra channels. And it's also a low-pass filter. So just to get the frequencies we want, not everything within 70 megahertz of our frequency. So that's kind of what we want to build, and I think that will be most of the components of a radio. So how do we get there?
Well, you've sort of explained how we get there. That's what's on the next slide.
Next.
We're almost, I think we're up.
Yeah, extensions and spin-offs. It was very easy to get distracted and think, oh, I could play with this and do this. So we just noted those down as things to do after we achieve this goal. Yeah, one obvious one is to expand to operating on more bands. Might not just be a handheld, we might make a console radio or something, get more power on it. And there's other things like the microcontroller that takes in IQ data and gives you a waterfall out. That's almost a self-contained kit that might be useful to people. And so we could spin things off like that. And you've probably got other ideas too.
I just threw that one in there, that idea, but I know Paul had a lot of other ideas as he was going through these boards, saying, oh, we could make one of these, we could make a general PAN adapter to plug into whatever, if we could get into that part of the various radios.
Sure.
And
Yep.
it's all very similar stuff, but we're just trying to steer him and me to keep focused on the one thing. Otherwise, we won't get anything done. But that's it in a nutshell, a technical nutshell. It's early days, obviously, for us. A lot of experimentation required, a lot of software dev to try things out, prove concepts, but it's ambitious for sure. But that's it's a long way from when I used to make radios with a 5Y3 rectifier and a 6V6 valve and an oscillator and an IF available too, and zap myself. But, and here we are trying to do this. So we succeeded then. I don't see why we can't now if we just keep at it and read all the application notes we can and then fix them and make them work. We'll get there.
Yep.
That's about it. We've got some things for you to look at. Thank you. Thank you. Thanks, Bob.
Cool.
Thanks for coming tonight. Come and have a look at these things if you want. Here's the
Okay,
bits and
okay.
pieces of our development. Thank you.
I was really interested in the whole thing. A lot of it went straight over the top. I hate to say that. But having said that, you are to be commended for your endeavours. Have we got an end date at all for a working prototype?
I would
Without putting you on the
imagine we'd be
spot?
back here 2 more times. That was what I was thinking. I reckon if we come back maybe in a year, we should
I was thinking a year, yeah.
we should be a long way down the track. Were you thinking earlier?
I was thinking about a year, yeah.
Yeah, that's what I'm
Okay.
thinking. And then surely by another year after that we'd have a product.
Hopefully I'm still around.
You'll be around.
I hope so.
The other thing that crossed my mind was the prices that you were talking about. We live in an amazing world where, whilst you say, oh, that's a little expensive, 50 years ago, 741 mil-spec op-amp was $100.
What?
And they used to put it in the safe at night to guarantee it was going to be there next day. So
I know the
we've
little
come a
741s.
long way, and this is all marvellous stuff.
Yeah,
So-
it's amazing what you can get for a great price now. It's, why not try and put it together ourselves? And,
Absolutely.
yeah.
Well, look forward to seeing a working prototype in the
Do our
not
best.
too distant future.
Oh well, we're keen, so we'll
As
push
is our,
on.
as is our custom, Graham and Paul, I'd like to present you
Oh.
on.
All right. Thank you very much.
You don't have to.
I didn't know this was a
Well,
custom.
I didn't know it
no,
was a custom.
you.
No.
Oh,
Oh,
nice.
absolutely. We
That's
like to
beautiful.
recognise
Thank
that.
you.
So
Thanks
hang
everyone
it with
for
the
coming.
test equipment or wherever.
Yeah, on the wall.
So round of applause, please. Thanks.
Thanks, guys.